Welcome to RCast, the official podcast of the RChain Cooperative. RChain is a complete concurrent blockchain platform designed for maximum efficiency at minimal computational and environmental costs by utilizing proof of stake. I'm Derek Barris, the Director of Content for RChain. We cover a range of topics on this podcast, from the foundations of blockchain in general to the specifics of RChain, including our foundational language, Golang, as well as issues in calculus, governance, security, and the forthcoming businesses and dApp development on our platform. Please check out rchain.coop to learn more about our platform, as well as information on becoming a co-op member.
Well, first of all, thank you, Derek, for there was a lot of coordination to get this one going, and so I really appreciate that. And thank you for hosting, and thanks to Isaac and Christian. I know it's a Thursday evening for Christian, so thanks for giving us your time. What we had hoped to talk about today was sort of the work that Pavel had done on TLA, and if he doesn't show today, we'll find another time and we'll talk about some other stuff. But TLA is the temporal logic of actions, and it's one of the go-to tools these days for people who are reasoning about concurrent systems. I would put it as probably a generation more mature than the spatial logic model checker, but both of them are sort of on the same footing in the sense that you write down a model and you write down the properties that you want your model to events, and then satisfy, and then you run the model checker, and the model checker goes and checks and sees if your model actually supports that. And Pavel was running into some issues in terms of the comms layer that were a little bit tricky for him. So he made up a model and then made up the properties that he was pretty sure we wanted to support, and was able to find some bugs this way and find relatively quick fixes. Now, it's a decent methodology, but there's a gap, and I wonder if you guys can kind of spot the gap.
So are you getting the gap between operational and axiomatic semantics?
But it's a little bit more down and dirty. The issue is that you might fix it in your model, but then there might be a gap between the model and the running code, right? So you might think that your actual in production code corresponds to the model, but it might not. So you've proven that your model is correct, but you haven't proven that the code that's in production is correct. So that's a serious gap, right? That's a wing and a prayer. And there's another methodological issue that I take with these kinds of things. I mean, first of all, I want to say it's an enormous improvement over the methodology where people are just slinging code and testing the hell out of it and seeing if, it's basically throwing the spaghetti at the wall and seeing what sticks, right? That isn't going to work in a concurrency setting. There's just too many ways for the system to go wrong.
Yeah, and it's a lot more useful and believable to prove theorems about your specifications for your code as opposed to just pass these tests.
Yeah, that's exactly right. So it's a big improvement, but it's still problematic in terms of the fidelity of the model to the production code.
What are the main sources of discrepancy between the program and the model, and why isn't there some way to ensure fidelity?
Oh man, you are asking exactly the right questions. So the main sources of discrepancy, and this is what I was trying to get at in terms of the methodological gap, is that the model is typically written in a language that's very, very different from the language that people write their production code in. So just to make this very concrete, if you look at the TLA model and you look at Scala code, they are miles apart. If you look at TLA code and JavaScript code, they are really miles apart. This relates to another well-known psychological aspect of development. Whenever developers have to face context switches, they lose flow And this is like actually quantified. So there's a guy, Mahalyi, Csikszentmihalyi, who has sort of described the notion of flow. But then if you go and look at, development studies, context switches, places where attention has to shift from one formalism to another or from one tool to another, that's where mistakes are committed. And so if you're going from your model to JavaScript or from JavaScript to your model, that's a context switch. And that results in a place where errors might be introduced. From a methodological point of view, we know there's a problem. We know that there's a problem in actuality in the sense that the code that's in production is not the model that was checked. And we also know that for developers going back and forth between the two, that's a context switch. And then finally, one of the real issues is that most Scala developers or JavaScript developers have no clue, and a lot of them have no interest in TLA unless they're really, really strapped because there's a serious bug. Then they might go searching for such a tool. So those are all the challenges that are associated with this kind of approach. I'm not disparaging the approach, I'm just simply listing out what are well-known and documented challenges of this approach. Now, how do we bridge the gap? Well, one idea would be to find a modeling language that could be used in production code. And then the next step would be to have your model checking be equivalent to type checking your production code. And this is essentially the proposal with the behavioral types. That's why we are interested in LADL, in the namespace logic, and in LADL in general. So with namespace logic for Rolang, which gives us a set of behavioral types which allow us to express and check a wide range of very, very impressive properties. And that fits into the methodology for normal developers. So in the case of RChain, where we can nail this down to specifics, Rolang is precisely a production language that can be used as a modeling language in the sense of the modeling language of TLA. And then the types that can be derived for Rolang using the namespace logic semantics can be used to express properties like the kinds of properties you can express with TLA. They're more closely related to the kinds of properties that you can express with the spatial logic model checker. So spatial logic formulae are very similar to the kinds of types that you can express, but the namespace logic is more expressive because it can see into the structure of names. And so it can do things that the spatial logic formulae cannot do. A really good example of this is you can define a notion of a compile time firewall. So at type checking time, so this is long before execution, you can assert that a particular process will only communicate on a certain set of names and not communicate on others. And in fact, you can unroll this over time. So you can have the collection of names or ports on your process be open in certain states, and then those which are open change in other states and then change yet again. So you can define these kinds of which ports are open at the type level before anything runs. So that hence the term compile time firewall.
So has RChain already been using the namespace logic in this way?
No. So the behavioral types come in Venus. After we go ahead and get the untyped version of the language defined, then in Venus we'll go ahead and produce the types. So in the Rolang 0.1 spec, I wrote down a draft of what the types would look like. It needs some more vetting in the sense that I wanted to make sure that the syntax for the types feels comfortable to developers. Syntax is a lot like UI in the sense that everybody has an opinion on syntax, and everybody wants to poke at it. A lot of people poke at syntax without a lot of experience. It takes a lot of experience to start to get a sense of why a particular syntax hangs together. Like I've committed most of the mistakes that people come to me and say, well, why didn't you do this or why didn't you do that? and it's like that story about the businessman. How did how did you get here experience? Well, how did you get your experience? Wrong decisions. That it's the same story. So anyway, so the we want the syntax of the types to also have the same kind of broad reach or understandability for the developers. So probably the version 0.1 of the types syntax will undergo some changes before we roll it out, and I want to give it enough time for people to get used to it. But I was really encouraged because the syntax for TLA properties is very, very similar to the 0.1 syntax for the Rolang type system that I provided, which is essentially just a syntactic rendering of the namespace logic types. So it was good to see that at least there's one developer on the RChain team under his own direction. He went off and used a tool that was very similar to the kind of tool that we're going to provide to the users of RChain. That's kind of the color and history of around the question you're asking.
Yeah. Well, who was that again?
Pavel. I guess he's a no-show today. I'm sorry. He wrote to me in Discord that he was going to be here, but anyway, so next time we can have this discussion with Pavel present, because what I would like him to do is to go through some specific examples. It's a situation where he felt the need to go and get additional support for his development process because he was running into a level of complexity where he needed automated support. And I think anyone who's actually done these kinds of distributed systems, they'll recognize and feel Pavel's pain. It is non-trivial. The literature on programming distributed systems and the kinds of errors people make is very, very much in support of that. Pavel's experience is very commonplace, not a one-off. So let me just stop there and check in and see if the spiel so far has made sense.
Yeah, it's making sense. Did you say that he essentially implemented TLA with namespace logic?
No. What I said. So TLA is an existing tool.
Yeah.
He wrote down a model in the TLA modeling language, and then he wrote down some properties in the TLA property language, and then he checked the model. So he's the human mediator between the production code and the model. You need Pavel's intelligence in order to render that TLA model.
I see.
Right, and that's the gap that I was talking about. So that's a really important question that you just asked. And this is the gap that we hope to eliminate. So what we want is that the code that runs in production is the modeling language. But in this case, it's not the TLA modeling language, it's Rolang, which is close enough to a process calculus that you can see the process calculus poking through the syntax. And so you can see how the types would be properties, like the TLA properties or the behavioral types from the spatial logic model checker or the behavioral types from namespace logic. That's the idea. I think what I'll do, and unless there are any other questions, because I wanted to go into some fairly deep dive details with Pavel. Part of what's really fascinating to me about this particular conversation is just the difficulty of getting the mathematicians and the developers into the same venue. We've been faced with this logistics problem like 4 times now. This is exactly the bridge I'm trying to build, is this bridge between the mathematicians and the developers, because there's some really interesting math here, right? I think the namespace logic in and of itself, and the spatial behavioral logics and the temporal logics of actions, these are all interesting mathematical entities. I think the LADL algorithm as a generalization of that is also a very interesting area mathematically, but it has really, really important practical benefits. It's one of these places where the deep, rich, beautiful mathematics has direct application to practical distributed systems. And so I really would like to have and broker that conversation between the mathematical community and the developer community, because I think they have a lot to say to each other. And so it's very, very ironic to me that we're having so many logistical problems here.
Yeah. Maybe different sleep schedules.
Yeah, something like that. Something like that. Not, but we can sort of take the conversation in a different direction. So there are a couple of other topics that I wanted to talk about from a brain candy perspective, and one of them is sort of the more recent research that's been going on with respect to LADL, because I'm not sure that the wider audience understands. There's lots of things that we've uncovered, and we're finding ways to kind of put this all together into a nice package. Just to remind people how LADL works, we start with two basic principles. One is something that was uncovered, gosh, I think it began in the 30s. It's called the Curry-Howard isomorphism, where people began to notice that there was this tight correspondence between the types in the simply typed lambda calculus and the formulae in intuitionistic logic. And they were able to give an isomorphism, a translation back and forth. But then as people dug into this idea, they were able to see that the correspondence was much richer. It wasn't just that the types corresponded, but that the proofs in intuitionistic logic corresponded to the simply typed lambda calculus terms, or the programs in the simply typed lambda. And the correspondence is even tighter. In intuitionistic logic, there's a logical rule called cut, and it's basically the application of an implication to the hypothesis. If you've been able to prove that A implies B, and you've been able to prove that A, then you can apply the implication A implies B to the hypothesis, and thereby derive B. This kind of application or cut, all proofs that use these things can be turned into proofs that don't use those things. So you can get a cut-free proof, and the process of deriving a cut-free proof is called cut elimination. And it turns out that cut elimination corresponds very precisely to beta reduction in the lambda calculus. So beta reduction is essentially you've got a lambda term that represents a function that is depending on an argument, and if you supply the argument, then you can get the result of the function. That application of the function to the argument is very similar to the application of a implication to the hypothesis. And so the cut elimination execution engine corresponds precisely to the beta reduction execution engine in the lambda calculus. So that turned out to be quite interesting, and people began to suspect that this way of looking at the world was much broader. And so in the 90s, Abramsky proposed to expand the scope of this. Instead of lambda calculus terms, you have processes, like processes in the pi calculus or other concurrency formulations, and then the corresponding logics there. So you should get a similar kind of thing, where you've got formulae that processes satisfy are equivalent to types that type check those processes. So this is the Curry-Howard isomorphism. On the other side, there's this notion of realizability. And this has to do with also with the semantics of proofs. So the idea of realizability is that the meaning of formulae should be exactly those computations which satisfy those formulae. So we realize the formulae as the terms that satisfy them. Another way to think about it, if you then sort of use Curry-Howard, the inhabitants of a particular type, so the terms that inhabit a type or satisfy a type, are going to be just those that are the meaning of the formulae. And when you take those two principles into account, then that forces a notion of logical semantics on you, because it's saying that formulae are the collections, whatever your notion of collection is, of terms that evince the particular property that the formula captures. So that's a whole bunch of stuff I just said. Let me stop, take a breather, and check in with Christian and Isaac and see if that makes sense.
Yeah, it definitely makes sense. And thinking about the different formulas that you can have in terms of just the collection of whatever objects it is that you're talking about, satisfying those formulas.
Yeah, and it relates to what I think developers know in their bones anyway, right? When you have a really simple type like int, you expect the inhabitants of that type to be all the integers. And so if you were to then go a little lower than just int, if you were to say, well, I'm modeling integers as church numerals, or I'm modeling integers as the Milner numerals or the Conway games or whatever, that those particular operational intuitions about what arithmetic are should be possible to write down a notion of type that would pick out just those computations. Right, so you would unfold int, which gives you no sense of structure, into a type that had more structure, and that structure would sort of force the shape of the computations in a particular way. So that then when you collected up all the computations that whose the structure of their behavior matched your description, that collection should be the meaning of the formula. And so as soon as you have that, then you can kind of give a sketch to the semantics of formulae. You can say, well, typically type constructors are going to be functors. A lot of them, especially if they're parametric functors, look like monads. If I look at the sort of standard collection gadgets like set or list or tree, those are all monads. And this is where a lot of the category theory starts to creep in, right? So we start to begin to suspect that monadicity captures a fairly decent notion of collection. But at this point, it's just a suspicion, right? We have to go and check that is the case for a wide range of notions of collection. Likewise, the whole idea of Levier theories allows us to express fairly sophisticated term languages and know that there's a monad that corresponds to them. So it looks like there's a monad that corresponds to your term language, the thing that's going to represent your notion of computation, and there's a monad that represents your notion of collection. And then we know something else, which is we know that the meaning of all the formulae are going to be collections of terms. So it would be the monad of collections applied to the monad of terms. That would be or composed with the monad of terms. That would be the meaning of your formulae. So now all we'd have to do is to figure out what the formulae themselves were. We can easily sort of come up with an intuitive notion of this. There's if you read Abramsky's paper, Computational Interpretations of Linear Logic, and also Abramsky and Vickers' paper on quantals and observational logic, and then also if you look carefully at Kairos' paper on spatial behavioral logics, and then if you inform that further with Abramsky's domain theory and logical form, you begin to realize that intuitively, formulae are just terms with holes knocked in them, right? So
yeah, exactly.
Yeah. And so that makes a lot of sense. And that's, it's like, and how you fill the holes gives you your collection. And it turns out that you can kind of write down a way of combining two monads to give you this terms with holes knocked in them, where you're collecting all of this in terms of your basic collection. That makes a lot of sense. And so now your semantics is, combine the two monads, like T plus C, and then it has to go from that combination over to CT. And the T plus C can be unfolded into, from a language theoretic perspective, it looks like all the words over T and C. There's going to be these funny words where, you know, you've combined a term and a, like one word in that sort of unfolding of T plus C is going to be T of C. And that's one of the words that shows up in that language. And the question is, well, how would you get from T of C to C of T? So if you assumed the existence of a distributive law where you can take a T over C to a C over T, and that's what the distributive law does, then you can also use the monadic laws to collapse all time where you have a C of a C that just becomes a C with a mult, and a T of a T just becomes a T with the multiplication of the monad. And so now, with all of that information, you can canonically construct a semantics. So that's, in essence, the LADL program. That's what we've said is, you know, the constraints of the principles of realizability and Curry-Howard force our hand with respect to the target of the semantics. They have to be collections of terms. Our intuitions about how we build a term language and how we build collections suggest that they should be monads, and that we combine them in a particular way. And if we do that combination, then we're forced. The semantics has to go from that combination to the target that we've identified. And sort of the minimal amount of, you know, axioms you have to introduce in order to make that go through canonically is the monadicity plus the distributive law. And so that's the sketch of the argument for LADL. Why LADL is an interesting idea, because if you can push that idea through in a reasonable fashion, then you get a very, very wide range of applicability. Suddenly you take, you know, what seems like this special case of the spatial behavioral logics and the namespace logics, and you expand it out to a whole range of programming languages and collections. But there are some interesting things that we've discovered along the way. One of them is that the distributive law doesn't exist. There are these things called no-go theorems. So there are certain kinds of monads, like the list monad, will not readily support a distributive law. Whereas, you know, a lot of the notions, the set-like notions of collections will support a distributive law. And so part of what we've discovered over the last several months worth of work is that the kinds of types we figure out, we're looking at, the collection part of it is going to be very set-like. It might be a multi-set, so we can probably make multi-set work, or it might be a notion of distribution, so like a fuzzy set, something like that. We can probably make something like that work. But the collection has to be very set-like under certain assumptions about you know, how we build terms and whether or not the monads are essentially tree-like or syntactical in a particular way. So I've said a whole bunch of stuff there. Let me shut up and check in with you guys and see if this is all making sense.
So I have a question about when you're talking about something that is like as opposed to list like, and you know, the list collection not supporting a distributive law. Is it something to do with the fact that it's an ordered data structure and set is unordered, or is it something along those lines?
Yes, that's exactly right. If you grind through the calculations, you need the commutativity of the set, because otherwise you have one path where you go around one way and you get a particular order of things. You go around the other way and you get a different order, and unless you can equate those two orders, you're stuck.
That makes sense.
Yeah, you don't get that.
A lot of the no-go theorems were about putting two notions of collection together, and in those cases there were like conflicts between certain algebraic properties of the collections. But in general, the term languages will in some ways have less or different structure than collections. So for example, in the row calculus, the par operator does form a commutative monoid.
Mm-hmm.
And so you need to look out for the similar theorems that talk about a conflict between commutativity and one of the properties that caused a lot of problems was idempotence. So that would be something pretty rare in a term language that we wouldn't have to worry about as much. Whereas in something like sets, you do have idempotence. It's a very difficult general universal algebra problem given two monads or two theories, whether there exists a distributive law between them. But it's a really interesting problem.
In terms of this very practical setting where we're interested in deriving type systems for computational, for models of computation, we don't have to solve the general problem, right? What we want is a broad enough notion of collection and a reasonably broad notion of computation. And that's still going to be so much better, right? I mean, we need to be able to support things like derive a type system for Scala or derive a type system for JavaScript. And in those cases, currently those type systems have been developed by hand. And the first versions of the Scala type system were unsound. And which is why they had to kind of go back to the drawing board and build Dotty and things like that, which, by the way, cost the industry a lot of money. And then JavaScript had no type system, and then so now you've got the big three, Facebook, Microsoft, and Google, all defining their own versions of type JavaScript, and each of those efforts costs tens, if not hundreds of millions of dollars if you do careful accounting, and they're not interoperative. You can't like take Dart and deploy it as ECMAScript or so on. So again, there's a lot of churn that it creates in the industry, and with LADL, if we get the scope of LADL fairly decent, I mean, it doesn't have to be solve these super hard problems in universal algebra to expand the scope out to where you can just press a button and derive a type system for these kinds of languages, and the type system is automatically sound and complete. That would save lots and lots and lots and lots of money for the industry. So that's why it's an important endeavor. There are other reasons to pursue it, and that has to do with viewing the type system as a query language. We're all used to going to GitHub and treating our code as kind of a data asset, but you really can't search GitHub on the basis of the structure of the code or the behavior of the code. And that makes GitHub more of a social thing, right? You have to know somebody who knows somebody, et cetera, in order to find code that does what you want it to do. And it could be a lot more effective if we could search GitHub on the basis of these objective properties about behavior and structure. You can get a lot of bang for buck in the sense of decent utility without having to solve super hard problems. I just want people to be aware of that. We're not necessarily putting Fields medal level problems on the critical path to providing good utility for the work that we're doing.
Yeah, so I guess in addition to like these main capabilities that you want a collection to support, like addressability and membership and that kind of thing,
yes,
I guess part of one of our main other criteria that will be a more mathematical one is a collection that has the right structure such that many languages distribute over it. And
yes,
hopefully that does not imply that the collection has not very much structure.
yes, yeah, exactly.
So that's the difficult.
Yeah, but again, you don't have to have a universal collection, although I suspect that set, because how many programming languages ultimately have a set data type as a part of them? Yeah. So that's a reasonable approach.
This is the whole reason I'm in the UK right now. Although I'm not yet answering the question of what is a collection, but more answering the question of what is a theory. And Marcelo Fiore has this big, like really impressive program over the past couple decades, augmenting the notion of an algebraic theory with substitution and typing and dependent types and polymorphism and everything that you would want a real algebraic theory of formal languages to have. And he's at a conference right now, but I've been studying his papers, and it's definitely what we need in order to have a full algebraic theory of these of the languages we want to use. And it's really nice mathematics. And actually, like the conference that he's at right now, he's winning the Test of Time award for the paper Abstract Syntax with Variable Binding.
Yeah. It's a lovely paper. It's a really lovely paper. Yeah.
It's very nice. So from talking with his students, I'm getting the feeling that he has this very big comprehensive view of this theory of theories. I think that he's going to be able to provide some very valuable insight about the LADL approach.
This is awesome. This is good. Also, yeah, I know that you'd mentioned that he has some interest in reflection, and I can,
Yes.
yeah. So I should probably at some point, if you and Marcella want to sit down over Zoom sometime, we can talk about the. So I uncovered this way of thinking about reflection where it relates to integration and differentiation. You have a 2-level type decomposition, then you've got holes in all your types, right?
Yeah.
So that's the differentiated form, and then reflection closes up the whole, so that's the integrated form. You can use those intuitions to derive some nice calculations. So
That sounds very nice.
On a completely different topic, since we don't have Pavel here and we do have a few minutes remaining, I found something really interesting, and I want to do a longer session on this, but I just want to toss it out there as a teaser. So it turns out that you can, in the same way that I was suggesting that reflection has analogies to integration and differentiation, a lot of the standard arithmetic operators have interpretations in the process calculi. So in particular, there's a notion that's an analog of square root. Like if I have a process calculus like the pi calculus or the rho calculus, I can say, and given a process inside one of these calculi, say p, then I can define the square root of p to be the process such that square root of p par square root of p is bisimilar to p. It's a crisp, clear definition. And then you might ask, well, when does the thing exist? And when it exists, can I calculate a closed form for it? I mean, maybe there are some bright people out there that can solve this problem, but I couldn't calculate a closed form. And this has to do with the nu operator. But with the rho calculus, you don't have a nu operator. So you can actually calculate a closed form. I was, waiting for my coffee this week, writing down a set of equations that would calculate the closed form. And I noticed that there was this particular place where something funny happens. So when you take the square root of a process that's of the form p par q, then you can push it through the par under the assumption that p and q don't interact. So what do I mean by that? Just equationally, what we're saying is the square root of p par q is equal to the square root of p par the square root of q under the assumption that p and q don't interact.
Yeah.
If they interact, what you really have to do is you have to go and pick out all the tangles or knots. And what do I mean by that? You have to find all of the terms that are potentially interacting at a name. So that means you've got opposite polarities using the name. So what do I mean by that? So you've got a term that's sending on the name and a term that's receiving on the name at a minimum. That's the smallest tangle. But you could have, so the smallest tangle is a red X. But it gets more tangled or knotted if you have races. So you could have 2 outputs on the term, on the name, and 1 input. Or dually, you could have 2 inputs and 1 output. That's an honest to God tangle. But you could have a lot more, right? It could be pretty pretty tangled. So you have to, in order to define the square root, you have to go and pull out all the tangles and treat them separately. And what you end up doing when you do this calculation is, again, you're creating a square root. So you're going to make a copy of the square root of the tangle and another copy of the square root of the tangle. And those will essentially you're going to push the square root through, but you're going to do it in a funny way where you adapt the namespace. So now you've got two copies of these races, which is a really interesting situation, right? Because what if one copy of the race goes one path, but the other copy of the race goes the other path? So when you put those in par, they won't be bisimilar to your original process because they took different paths. To define the square root, you need to force the two copies of these square roots of the races to choose the same races, choose the same winners of the race is what I really mean. So we just stop there and see if that's making sense.
Isn't it kind of like unnatural to impose some kind of restriction on the future behavior?
No, it isn't. And in fact, that's exactly what Casper does.
Oh.
Casper is a protocol that forces the agreement on the winners of all the races. So that gives you this really, really nice equational characterization of consensus in this setting. I mean, it's not going to be this consensus, possibly in other settings, but at least in this setting, consensus means that you can guarantee that the copies all agree on the winners of the race. And now here's the really interesting trick. So you can go back to this annihilation style notion of reduction. Let's just look at the simplest possible red X, right? I've got a send and a receive. We've got, let's say, two sends and one receive. And we've got two copies of that. So there's some name X. And X is really the quote of a process. So to pick out that it's X as opposed to Y or Z, we need some component of X to be its identifier. So in other words, P is going to be structurally equivalent. The process P that X is the quote of is going to be structurally equivalent to some P prime, which is the identity part, the thing that picks out that it's X versus something else. And then another part that is designed to force the agreement on the winners of the race. So now you define your COM to happen only when they agree. And then the other piece of it is because it's recursive, you're going to have to keep repeating that at the next level and the next level. So it completely, until you get down to the origins of your names, right? Your names are now going to, you ultimately have to ground out at a set of names over which you can get agreement on these tangles, without having to go into any further COM events. So the fact that you're doing this in this multi-layered or recursive style, together with this requirement that you have to agree on the winners of the race, completely pins down the shape of your consensus processes. So the square root is forcing a decentralized consensus on two copies. The nth root is going to give you a decentralized consensus on n copies. Is this making sense? Are you following what I'm saying?
The nth root would just be like n processes written in parallel that somehow all reduce to this original process, or maybe there's
so when you put them all in parallel, they're bisimilar to P.
Right.
Yes.
Okay.
So this notion of nth root is actually giving you an equational characterization of what consensus means, at least in this setting.
Yeah, that's awesome.
I wasn't expecting this at all. I was just pushing the math through. And it didn't occur to me, what is the meaning of this? It's like, some far-fetched analogy from math is like, what was Ramanujan thinking when he was coming up with these theta functions, right? Who would ever think it would have any sort of applications? And similarly here, I was just following the math, right? and then the interpretations kind of leap out at you later. And this is methodologically important, I think, right? It's important that we have something like the math that leads, even when our intuitions fail, or in anticipation of our intuitions, and then our intuitions catch up, and we go, "Oh, wait, this is actually saying something important," right? So I think that's an aspect of having the math and being able to important perspective.
Yeah, that's amazing. That's an amazing phenomenon of abstract math nowadays, is that you can take like remarkably naive analogies and they end up saying something quite significant.
Yes, that's exactly right. I wholeheartedly agree.